Hello, everyone, and welcome to phyloseminar.org. This is talk number 2 in a series of 4 talks introducing phylogenetics by Master Expositor Paul Lewis. I've already introduced Paul in the first talk, so I'll just let him get started. If you want to ask a question, you can either tweet at phyloseminar or type your question into the live chat box to the right of the video on YouTube. Thanks, Paul, and take it away.
Thanks, Eric. So today I'm going to be talking about substitution models, building upon the brief discussion of the Jukes Cantor model that I started in the last part. I'll be referring to things I've talked about in part 1, so you might want to review part 1 if you haven't seen that part before watching this part. So I'm going to be talking about 5 common substitution models. This is not all the substitution models in common use, but it's a representative 5 that I think will help you understand the others once you understand these. Then we'll talk about adding rate heterogeneity to these models. And then I'll switch to talking about codon models, and then eventually end up talking about empirical amino acid models. And in between, I'll talk about this process called diagonalization that allows us to get transition probability matrices from more or less arbitrary rate matrices. So let's go through a survey of 5 common substitution models to start with. So we've already talked about the Jukes Cantor model in part 1. Here's the rate matrix for the Jukes Cantor model. These are instantaneous rates of change from either of any of the 4 bases on the left to any of the 4 bases on the top. And there's only one parameter in this model, beta, which is the substitution rate for any kind of substitution. So 12 of the 16 elements of this rate matrix are beta, and the other 4 along the diagonal are -3 beta. And the -3 beta represents the rate at which A, basically if A is changing, for example, to C, G, or T at a rate beta, then that means that the amount of A is dropping at a rate of -3 beta, or the rate of 3 beta, and it's -3 beta because it's dropping. So this is a rate matrix and not a probability matrix. If it were a probability matrix, then the rows would sum to 1, but it's a rate matrix, and so the rows sum to 0. So the diagonal element is always the negative of the sum of all the other elements in the row. So this is a single parameter model, 1969. A few years later, about 11 years later, whoops, I was going to review a little bit from last time. So from part 1, I mentioned that I derived the expected number of substitutions per site. So this is how we, usually the units that we use for branch lengths are an expected number of substitutions per site. And the branch lengths are, of course, related to the rate. So if you have a higher rate of substitution, then the branch length would be, for a given amount of time, the branch length would be longer. You'd expect more substitutions if the substitutions are coming at a faster rate. And then if the time is larger, you also expect a larger branch length. You expect more substitutions if you have a given rate the process goes for a longer time. So in the Jukes Cantor model, there's a very simple relationship between the instantaneous rate and the time and the expected number of substitutions that we use for the branch length. But I also, in part 1, talked about how you derive these formulas for transition probabilities. We need the transition probability formulas for calculating the likelihood of either 2 sequences, if you're interested in getting an estimate of the evolutionary distance between 2 sequences, or the likelihood of a full tree if you're interested in that. So the transition probabilities in the Jukes Cantor case, there are only 2 different versions. One describes the probability of getting the same state at the end of a branch as you have at the starting point of the branch. And this formula gives you the probability of seeing a different state at the end of the branch. And each of these formulas have the branch length V in the formula. So as the branch length gets bigger, if the branch length went to infinity, this whole term would drop out, and you would end up, if you evolved for an infinite amount of time, you would end up with a probability of 1/4 of seeing either the same state or a different state at the end of the branch. The equilibrium frequencies, thus, are the frequencies you get if you run this process for a long time. And for the Jukes Cantor model, this very simple model, those all will be 1/4. And so if you run it for a long time, you end up with the 1/4 probability of seeing any particular state, regardless of what state you started with. So about 10 or 11 years after the Jukes Cantor model was introduced, Kimura introduced this model called the K80 or the K2P model. It's called the K2P model sometimes because it has two parameters rather than one. So the two unknowns in this rate matrix are alpha and beta. If you were to put actual numbers in for alpha and beta, you would get actual numbers in all 16 elements of the rate matrix. So there are only two things that you can play with, two quantities you can play with, or parameters in this model. And Kimura recognized that there's usually many more transition type substitutions than transversion type substitutions. So he gave a different rate to the transitions than the transversions. So the transitions are type substitutions, or substitutions between two purines, such as A and G, or between two pyrimidines, such as C versus T. And so there are four elements of this rate matrix that have alpha as the rate, the transition rate, and the rest of them have betas, and then the diagonals, of course, are the negative of the sum of all the other elements in each row. So you see this rate matrix in one of two ways. You can either see it this way, where you have alpha and beta as the parameters, but there's also a different way that it's represented that's perhaps more common, and that is using beta and kappa, where kappa is what's known as the transition-transversion rate ratio. It's the ratio of the rate of transitions to the rate of transversions. So we can relate the two parameterizations by this formula here that shows kappa as a function of alpha and beta. So in this version of the rate matrix, we have kappa beta in all of the slots that are designated for transitions, and then just beta for the transversions. And so this parameter still has two parameters, or this model still has two parameters. It's just that the parameters are now kappa and beta, but it behaves exactly the same way as the other parameterization. So I want to talk a little bit about the distinction between the transition-transversion rate ratio and the transition-transversion ratio. This comes up in several different models, and so it's good to talk about it for this relatively simple model. So if the transition rate is alpha and the transversion rate is beta, and if we assume that these are the same, alpha equals beta, then the transition-transversion rate ratio is 1, and that's because alpha divided by beta, if those two are the same quantity, then you just get 1. So that's the rate ratio. So what is the transition-transversion ratio? This is very confusing in the literature, and sometimes people use the wrong term for what they're talking about. The transition-transversion ratio is 1/2 in this case, and this is the ratio of the number of transitions you would see over a short amount of time over the number of transversions that you would see. And because there are more ways of generating a transversion, then you end up with a transition-transversion ratio of 1/2, even though the rate of transitions is the same as the rate of transversions. I'd like to use an analogy here. Let's say we have a factory that's making shoes, and let's say there are two different kinds of sneakers, and one kind of sneaker, the model is called a transition, and the other kind of sneaker that this factory makes are called transversions. And so the transitions are, here's a cobbler here making transitions type shoes at a rate alpha, and you got two workers, two cobblers making transversion type shoes, and they work at a rate beta. So let's say that these workers all can produce their shoes at the same rate. Because we have two workers, two cobblers that are making transversions, there are going to be more transversions made by this factory at the end of the day than there are transitions. And there, in fact, there's going to be 1/2 as many transitions made as there are transversions, because we have twice as many people making the transversion model. So that's the basic idea, is that because there are more ways of getting a transversion, then you'll have more transversions, assuming all of the things are equal. In reality, in sequences, the transition-transversion ratio is usually greater than 1, because the transitions usually greatly outnumber the transversions. The transition rate is actually much higher than the transversion rate, and so sometimes you can get transition-transversion rate ratios greater than 10 or 20, even 20 sometimes. And so in reality, the transition-transversion ratio is rarely less than 1. But this example is just to show you that what I mean by the difference between these two. So let's move on to the third model, the Felsenstein 81 model. This model goes back to this famous paper by Felsenstein that basically set the stage for calculating likelihoods in phylogenetics. It's a very important paper, and not only did Felsenstein describe how to calculate a likelihood for a tree using sequence data, he also invented a new model at the same time, and we call that the F81 model usually. So this F81 model has 4 parameters. and I'll designate those pi A, pi C, pi G, and mu. So these are three of the four base frequencies, and this is sort of a general substitution rate. So why don't I include pi T? And that's because if you know pi A, pi C, and pi G, you automatically know pi T because the four base frequencies have to add up to 1. So there's only 3 of these you can play with, and it's arbitrary which one you leave out, and I had just left out T arbitrarily. If you know these 4 numbers, if you have actual values for each of these 4 quantities, then you'll have actual values for each of the 16 elements of this rate matrix. So this model has 4 parameters. At this point, I want to start emphasizing that one of these parameters in the rate matrix is usually present in every element. So if you look at mu is present in every element of the rate matrix, whereas the others are only present in some of the elements of the rate matrix. So mu, the one that's obtained that's present in every one of the 16 elements is a parameter that's obtained from the branch length. So the branch length determines one of these parameters of the substitution model. The other parameters of the substitution model are usually global parameters that apply to all branch lengths. So pi A is the same for the whole tree normally. It doesn't change from branch to branch, but mu will be a different value for each branch. And I'll talk in a minute about how you get mu from the rate matrix or from the branch length. That said, this is an unusual rate matrix because it's got the base frequencies as part of the rates. And so the frequency or the rate at which you get C's, given that you started with A's, is pi C times mu. So there's this general substitution rate that's sort of the average rate, and then that's modified by the base frequencies. And this allows the base frequencies to be different, the equilibrium base frequencies to be different than 1/4. So the other 2 models we've discussed, the equilibrium base frequencies are all 1/4. They're all equal. This allows unequal base frequencies, and the way to do that and keep the model time reversible is to put the base frequencies that you would like the model to hover around in the rate matrix itself. So this doesn't look on the surface to be time reversible. Time reversibility means that the rate of going from A to C is the same as going from C back to A. So it doesn't matter which way you go along a branch, which direction you go, you get the same probability. So it doesn't look on the surface to be time reversible because here we have pi C mu for one direction and pi A mu from the other. But you have to remember that the rate at which these substitutions occur depends a lot on how many of the starting state are present. So if there's a lot of A's, let's say A is twice as frequent as C, so pi A is twice as great as pi C, then that means that there are going to be twice as many A's to start with that are changing to C's at this rate, and only half as many C's that are changing at the faster rate. And so the 2 cancel out, and you end up with basically a symmetry in the rates of change forward and backward. So you might have noticed that I switched from using beta to mu as the general substitution rate parameter. And the reason I did that is because I want to throw in this slide to show that JC69 is a special case of F81, and it's also a special case of the K80 model. But to see that it's a special case of F81, let's just set all of the frequencies, the equilibrium frequencies, to 1/4, which is true of the Jukes and Cantor model, and see what we get. And so in that case, we get 1/4 mu in all the off-diagonal elements. And so before, when I showed you the rate matrix for the Jukes and Cantor model, I had betas in all the off-diagonal elements. And so these 2 are really the same model. It's just that 1/4 mu equals beta. This is kind of like saying expressing the rate at which you're going in a car in miles per hour versus kilometers per hour. You're going the same speed in both cases, but the units that you're using are different. And so here, it's just that mu is 4 times greater than beta, so we have to divide mu by 4 in order to get the speed the same for the 2. So the next model that came along is the Hasegawa, Kishino, and Yano, and they model in 1985, or the HKY85 model. This is a very popular model, and it basically combines the F81 model, so you can have unequal base frequencies, equilibrium base frequencies, with the K80 model, so that you can have transitions that outnumber transversions. So it has a kappa for the transition rates, and it also has the base frequencies in for each of the in each of the instantaneous rates, so that you can have unequal nucleotide frequencies. This model has 1, 2, 3, 4, 5 parameters. So we have the 3 nucleotide frequencies, and again, one is left out because it can be determined by subtraction from the others. And then we have a kappa and mu. And as I said before, one parameter is present in every element of the rate matrix, and that one is the one that's determined from the edge length of a particular model. And so even though you might have a Jukes-Cantor model that has seemingly one parameter, you have to remember that that parameter is different. You have basically that model applied to every edge of the tree. And so in a 4-taxon tree, you might have 5 edge lengths, and so you really have 5 Jukes-Cantor models, each of which has a single parameter. So in this case, if you were applying an HKY model to a 5-taxon unrooted tree with 4 edges, you would have basically these 4 parameters, which are global, that apply to all the branches, and then these would be different for each of the 5 branches. So you'd have 5 plus 4 is 9 total parameters in such a model. So I want to spend a minute or two explaining how do we figure out what mu is if we know what the branch length is. These are related. So the higher the rate mu is, the larger the branch length will be, because you expect more substitutions for higher rates. But how do you actually estimate mu given an edge length? So let's see how we might do that. So let's start by noticing that if you started with an A at a particular site, then the rate at which A changes to C, G, or T, the rate at which A changes to anything else, is just the sum of these 3 rates. So it changes to C's with this rate, and G's with that rate, and T's with that rate. So the sum is just the sum is just the total rate at which you move away from A over time. And then conveniently, the diagonal elements summarize this, because the diagonal elements are always the negative of the sum of all the other elements in the row. And so we can just multiply this diagonal element by -1 and automatically get the sum of these elements for this row. So this gives us the total, the negative of this element gives us the total rate at which we move away from A. But we have to take into account the fact that A's might be greater or lesser in frequency than the other nucleotides. So if A's are really abundant, then this rate becomes more important, because there are many A's that can possibly evolve away to other nucleotides at that rate. So let's our mean rate of substitution is going to be a weighted average of the 4 total rates, where you get one of the total rates from each of the diagonal elements. So this total rate we're going to multiply by pi A to acknowledge the fact that we're starting with an A. So this is the probability of starting with an A, and this is the rate at which you get a substitution given that you started with an A. This is the probability that you start with a C, or that you have a C at a site, and this is the rate at which you get a substitution given that you have a C at the site, and so on. So our lambda here is going to be our average substitution rate. It's an average over the 4 possible total rates that I've circled here. So the edge length, the expected number of substitutions, expected number of anything is just the rate times the time. If you drive your car at 100 kilometers per hour for 1 hour, then you've gone 100 kilometers. And so the 100 kilometers is the number, and then the rate is the kilometers per hour, and the time is the number of hours that you've been driving. And so the number of substitutions is going to be the rate of substitution times the time that substitution process has been operating. So lambda times t will give us the expected number of substitutions for that overall rate and that time. And so all I've done is taken our formula from the previous slide and put a t in each of these cases, multiplied through by t. And that formula can be simplified somewhat to this formula, the second line here. Just using a little algebra, we can reduce it to this, so it's a little bit more compact. And I've done all of this just to show you that there's a relationship between the expected number of substitutions, which is our branch length, and the substitution rate mu. At least the substitution rate mu times the time is related to the branch length. So all we have to do to get an estimate of mu t is just to move this whole mess to the other side, divide through both sides by that, and you get v over that whole mess is equal to mu times t. So if we have a branch length and we have values for all of these parameters, we can obtain mu t from that branch length. So if you want mu by itself, you're in a little bit of a quandary because the mu and t cannot really be separated. Our data gives us information about the number of substitutions, that is v, but it doesn't give us information about the rate or the time. The rate, you could get the same number of substitutions with a high rate in a short time or a long time, and a high rate in a short time or a low rate in a long time. And so to basically just standardize things, we often express our times in our tree in terms of the expected number of substitutions. So the branch lengths are not times, they're expected number of substitutions. And when you make that assumption, which is just an arbitrary convention, then t becomes equal to v. And so we're sort of fixing or the units of time to be substitutions. And that means that the t and the v both cancel out. One's on one side, one's on the other. You can divide through both sides and those go away, and you just get mu equals 1 over this whole mess here. So if you want to have to use this convention that we're going to measure time in units of expected substitutions per site. So in each model, the parameter that can be obtained from the edge length is the one that you find in all 16 cells of the rate matrix. And keep in mind that sometimes rate matrices are presented without that parameter. Because it's present in all the elements, just leave it out. So if there is no parameter that's present in all 16 cells, then you have to mentally add that in yourself. Move on to the final model that we're going to talk about today, the fifth of the 5 common models that I plan to talk about in the model. This was invented by Tavaré, or described it by Tavaré in 1986. And it has this many parameters, 3 base frequencies, and a general substitution rate, so that mu is present in all the elements of the rate matrix. Because it's getting complicated, I'm just replacing with dashes here, or m dashes, but you can, it's basically just the negative of the sum of the other elements on the row, so you know what that is. So mu is that general parameter you get from the branch length, and then these things, A, B, C, D, and E, are exchangeabilities. And just to avoid confusion, E is often that, number 2.7 something that is the base of the natural logarithms. In this case, it's just a letter that I'm using to represent one of these exchangeabilities. There are actually 6 exchangeability parameters. Just generalizes the K2P and the HKY model. So instead of just having transitions be different than transversions, we can have a potentially different rate for every possible one of the 6 different kinds of substitutions. So in order to keep the model time reversible, and I'll talk about that in just a minute, these exchangeabilities are symmetric. So this A has to be that same as that value. This has to be the same as that value. That has to be the same as that value. So that just the exchangeability part of the matrix is symmetric across the diagonal. We don't have to include F, or we shouldn't include F in our list of estimable parameters, because these are relative rates. They're relative to this general rate. And so basically these just modify the mu. So if C is 2, that means that mu is effectively twice as great as the average rate. This substitution is evolving at twice the average rate. If E, for example, is 0.5, it means that this substitution is evolving basically at half the average rate, all other things being equal. So because these are relative rates, we put a constraint on these. And one of the constraints could be that just F is set to 1 and everything else is relative to F. But more commonly, the constraint is that they all have an average of 1, or a mean 1, or a sum of 1, some kind of constraint that means that there are only 5 that you need to estimate in order to get the 6th one. So we'll only put 5 in our list of parameters, and then 6, 7, 8, 9 parameters total. One of these is obtained from the branch length, and the other 8 are global parameters normally. So the GTR stands for general time reversible. And so I want to talk once again about time reversibility. So time reversibility means that the probability of starting with an A and then ending up with a G at the other end of a branch with length V, which if we're following this arrow, that's what we're doing, is the same as starting with the G and going backwards in time so that you end up with an A at the other end of the same branch with the same branch length. So if these two sides of this equation are equal, then that means the model is time reversible. And time reversibility allows us to root the tree at any particular point. We don't have to worry about where the root of the tree is. So it has some practical advantages, but it's not a requirement for substitution models that are used in phylogenetics. It's just a commonly feature of these models. And this is the most general model that is still time reversible. So let's summarize the 5 models that we've talked about: the GTR model, HKY85, K80, F81, and JC69. These arrows show that each of the models can be made equal to a less general model or more specific model. The GTR model becomes equal to the K85 model if you set A, C, and D, 3 of the exchangeabilities, to 1, which means that they basically just disappear from this list. And if you set the other 2, B and E, to kappa, then that means that you end up with just the base frequencies, kappa and mu, which is, basically you've got these 3 here plus kappa is made from some of these parameters. HKY85 can be converted to K80 model by letting mu equal 4 beta and setting all of the base frequencies to 1/4. So that eliminates these guys because you're setting them to particular values. They're not parameters of the model anymore, and we're just exchanging mu for beta now. You can also take an HKY85 model. If you set kappa to 1, then you basically just knock out the kappa parameter and you get F81 model. And then each of these models can go down to the Jukes-Cantor model by either setting kappa to 1 or by doing the same set of substitutions we did up here. We're just sort of delaying these substitutions until later, switching the kappa and these guys in order to go from F81 to JC69. So these are all part of the GTR family of models. The GTR is the most general, the JC69 is the most restrictive, and so they just vary in the number of free parameters they have and how flexible they are at modeling evolution. So I want to switch now to talking about rate heterogeneity. If you take a look at some sequences, here's some sequences from the green plant rbcL gene. What I've done is for these organisms here, I've just shown you the sequence for Kara at the top, the full sequence, and then everybody else has got a dot if it's the same as Kara at that site, or if there's a substitution, you can see the substitution this way a little better. So you can see that third codon positions tend to have more changes than first and second codon positions in this representation. It sort of makes it clear that there's a regularity in the high rate sites. Here's the amino acid translation for ZMAs that just shows you where the codon boundaries are. And the point of this slide is to show you that in this sequence, some sites you see all 4 bases, A, C, G, and T, are represented in this one column, one site pattern. Whereas in many sites, there's only an A, everybody has an A, for example, at this site. So only one base is observed. So this is obviously a lower rate of substitution than this, given that these are all evolving for the same amount of time. This has to be evolving slower than that because you've had a lot of more changes at this site than this site. So what we're going to try to do now is add to our models this ability to model the different rates that are going on within a sequence, among sites within a sequence. The most straightforward way to do this would be to just, if you know that the third positions are evolving faster than the first and second positions, is just to put all the third positions together, call that a subset of the total set of data, and then put the first and second positions in a different subset and give them each a relative rate. So R1 is going to be the relative rate that applies to subset 1, and R2 applies to subset 2. So there are twice as many positions here because we're combining first and second codon positions as there are in this subset. So we have to take that into account when we estimate our relative rates, because we want the average rate or the mean rate, relative rate, to be 1 so that we don't change the meaning of the branch lengths. So all we're trying to do is model heterogeneity. We're not trying to model the branch length itself. We're just trying to create modifiers of the branch length that will scale the branch length up or down. And so we want the mean of those modifiers to be 1. And since there's twice as many sites in this first category, then we're gonna the weight that we're going to use for this first R1 rate is going to be 2/3, whereas the rate or the probability for the second rate is going to be 1/3. So we're going to use a weighted mean in order to calculate this. And so that means that R1 and R2 are going to reflect the fact that this weighted mean has to be 1. So how are these used? Basically, we just need to calculate the site likelihoods, multiply all those together to get the overall likelihood, as we talked about in part 1. The Y's here represent site patterns. So this is the pattern of nucleotides in one column of that matrix I just showed you. And this is the rate that's being applied to that particular column. So this is the site likelihood, the probability of the data for site 1 given the rate for this first category. And we apply that rate to all of the site patterns from the first and second codon positions, all 88 of them. And then there's 44 third positions. And so we're applying rate 2 to those. And so these rates have the effect of basically scaling the tree up or down. And so the third positions are evolving at a faster rate, and basically this R2 is going to be something like 2.7549, whereas R1 is much smaller, 0.12255. And if you throw those into the formula, you see that these indeed have a mean of 1, but this one is about 24 times greater than that one, which means that when we're calculating the likelihood for these third position sites, it's as if we're doing it on a tree that's really much bigger, scaled up compared to the tree that we're using, the branch lengths that we're using when we're calculating the likelihood for the first and second codon positions. And so in practice, you would get these R1 and R2 by maximum likelihood if you're using a maximum likelihood method. And so you would find the values of R1 and 2 that make the data least surprising, as we mentioned in the last part. And that's what these values are in this case for those 132 positions that I showed you in the previous slide. So the site-specific rates approach, how do you actually implement this if you're calculating the likelihood? So I'll go back to the Jukes Cantor model since we've already talked about the formula for transition probabilities. So we have this formula. If you have the same state at both ends of a branch, you have this formula. If there's a difference across a branch, and then basically I don't have the branch length here, but I have the rates that were in the rate matrix. So this is what you would use if rate homogeneity were assumed, if you're assuming the same rate for every site. But if you're assuming this site-specific rates approach, then for the sites that are in subset 1, you're going to stick in R1 here as a modifier of beta. So you're going to basically scale beta based on the value of R1. And for subset 2, you're going to stick in R2. And so we only have to calculate the likelihood once for every site, but the rate that we're using for that site changes depending on the site, depending on this predefined categorization of sites into subset 1 or subset 2. So you can sort of think about this. This is my sort of silly analogy. Let's say that this is a sort of a leader of a PI in a large lab group, and this is all of his postdocs and students, and he's going to buy lab coats for each of these students, and he's going to divide them up based on the color of their head. So you've got some criterion for dividing these postdocs and students into 2 groups, and he's going to buy, you're going to find the average size of each person and then buy a lab coat that's that average size for that particular group. And so the problem with this is that every person in a particular group has to wear a coat of the average size, and that's too big for some people and too small for other people in that group if there's a lot of heterogeneity within the group. So it behooves you to sort of pick the groups well to start with if you're going to use this site-specific approach. The good thing about this is that it doesn't cost very much. You just need to buy 1 coat for every person, and we'll talk about the alternative in a minute. But we just have to buy 1 coat for every person, and this is basically referring to the fact that we only have to calculate the likelihood once for every site. But we're using this average modifier for every site in that group. So if we don't do a good job of partitioning our sites into groups so that there's still heterogeneity within each group, then we have this problem that the model still may not fit very well. So let's contrast the site-specific approach where we predefine what rate every site is evolving at. We at least assign the sites to groups based on what we think the rates will apply. Let's switch to a mixture model. And the nice thing about mixture models is that you don't have to worry about pre-assigning sites to particular groups. You don't have to decide how many, you sort of have to decide how many groups there are, but you don't have to decide what sites are in those groups, because all the relative rates that are being used are applied to every site. So here we have an alignment It's a mixture of first, second, and third codon positions, and I've just got the cursor here over this particular site I. So let's talk about calculating the likelihood for site I. So instead of assigning this to a particular category and using R1 or R2, we're going to just calculate the likelihood as the average of the likelihood over every possible rate that we've defined. So if we have k different rates in operation, we have k different R values, modifiers for that rate, the average rate, and we calculate the likelihood k different times. And so you can see that this is going to be more costly than the site-specific approach, because for every site we have to calculate the likelihood k different times, which is going to be expensive computationally. But the beauty of it is that whether this is a fast site or a slow site, one of these R's is probably going to apply pretty well. And so the model's going to fit on average better than if we were to make the wrong choices about how to divide sites up. So even if the first and second codon positions on average evolve slowly and the third positions evolve quickly, there's always some sites in the third positions that evolve slowly and some first and second position sites that evolve quickly. And so you're going to make some mistakes along the way. And this model has the advantage that you don't have to pre-assign things, and it will probably present one of these rates that works pretty well, and therefore the likelihood can be largely determined by that particular rate. So there are two different common mixture models in use. One is called the invariable sites model, or the I model, and the other is the discrete gamma model, or the G model. So these two different models are they're both mixture models. It's just that they define the number of rates, and the probabilities of rates are defined a little differently. So if our PI was buying lab coats for everyone and using a mixture model approach, then you would say, okay, I'm going to give you each 2 coats, use the one that fits the best and throw away the other one. This costs twice as much for me, but on average leads to better fit for you. So I've determined the 2 sizes of coats based on the distribution of your sizes. And so now the smallest person can choose to use the small coat and throw away the big coat, and the bigger people can choose to use the big coat and throw away the small coat. But the lab head had to buy 2 coats for every person, so it's more costly, this approach, but it ends up fitting better in the end, because each site in this case, or person, can choose the coat, or basically the rate, that fits them best. So
I love that metaphor, but it just makes me think, I mean, you're not really throwing away the other coat, right?
Yeah, there's always a downside to every analogy, and that's the one here. We're not really throwing away, we're just not using it as much, I guess I would say.
Yeah, the likelihood will be small enough, it will probably not change anything.
Probably will be negligible, yeah, or maybe negligible, and one rate will sort of dominate. So that's I expected that someone would ask that question at the end, but it's good to sort of clear that up right away. So anyway, so let's talk about the 2 different approaches to the mixture model approach. So the invariable sites model says that a certain fraction of sites are assumed to be invariable. So one of the rates is going to be 0. We'll just make R1 arbitrarily the rate that's 0, and a proportion of sites P and var has that rate. So the component of the likelihood related to these is P and var times the likelihood given that rate 1, which is 0. And then there's this other component, which are the variable sites. So 1 minus P and var, that fraction of sites is variable, or assumed to be variable, and we have this value R2 that is the rate at which we assume those sites are evolving. And so because our rate mean has to be 1, then it turns out that R2 should be 1 over 1 minus P and var. So there's a little bit of confounding of the proportion of invariable sites with the rate, this R2 rate. This just shows you that indeed the mean rate is 1.0 if you use these particular R1 and R2 values. So it allows that for the possibility that any given site could be variable or invariable. But the downside is that it assumes that all the variable sites are evolving at the same rate. So this is good for sort of a crude way of doing rate heterogeneity, where you have a lot of sites that are under very strong stabilizing selection and don't change at all, and then they're constant sites basically, and then some sites change rather quickly. So if a site is constant, that means that you have all the tips have the same state, and both terms will contribute to the likelihood, because it's possible to explain this with a site that's evolving at rate 0, because you have everything is the same at the tips. But for variable sites, you don't even have to calculate this likelihood because you know that that's got to be 0. You can't have a change along the tree if the substitution rate is 0, and that's what R1 is in this case. And so we know that's going to be 0. We only have to calculate the likelihood, assuming that's variable, and multiplying by this probability being variable to get the likelihood for the variable sites. The alternative to the I model is the discrete gamma model that was introduced by Yang in 1994. No relative rate is exactly 0 in this model, and all rates are equally probable. So instead of having one rate that's 0 and having a different proportion of sites that are evolving at that 0 rate versus non-zero rate, we have all 4, or how many rates you want, how many categories you want. They're all evolving at different rates, but they all have the same probability. So we assume a fraction 1/4 are evolving at R1 and 1/4 are evolving at R2, and so forth. If our likelihood is based on 4 different relative rates. So we can use a different number than 4, but 4 is a common number to use for this discrete gamma model. So so how do we get these rates in this case? And the last time we set one of them to 0 and the other one was determined because we set one to 0. Now we're going to get them from a gamma distribution in this case. So if we have a continuous gamma density curve, we can divide it into 4 chunks if we have 4 categories, and each chunk has an equal area. That's how we get the 1/4 of the distribution in each category. So these boundaries are determined by the area under the curve. And so the area under here is 1/4, 1/4, 1/4, and 1/4. If we had 5 categories, we'd want these areas to be 1/5 each. And then the relative rate themselves are determined as the mean or the median of each of these categories. And so here I've shown you where the mean is for each of these categories. So even though this category goes from this point to infinity, the mean is still a finite number, and it's 2.386 in this case. And so what we're saying is that for every site that we evaluate, we're going to try each of these different values, and we're going to make the likelihood the average likelihood for each of these 4. So fast rates will be able to take advantage of this one. Slow rates will be able to take advantage of that one. And the other thing that I need to mention is that these rates can change as the analysis proceeds as well, because the shape of the curve determines how extreme these values are. And so this model actually just adds one more parameter, the shape parameter, and the shape parameter determines the shape of the continuous gamma distribution that's determining all of these rates. So you can if you make the shape large, then this gamma density curve is rather concentrated over 1.0 because remember the mean of these relative rates has to be 1. So we use a gamma distribution that has a mean of 1 so that these relative rates will model heterogeneity and not change the average rate. But if you make the shape parameter 1 or less than 1, you can change the shape of this gamma density considerably. And if you make it a lot less than 1, then what you end up with is a case where most of the sites are evolving very slowly, so the density is very high here. Most of the sites are evolving slowly, but a few are evolving very quickly, and those make the average rate what it is. So the average rate is determined by a few sites, mostly determined by a few sites that are evolving 4 or 5 times the average rate, whereas most sites are evolving much less than the average rate. So if you're estimating the shape parameter when you're using this model, the larger shape parameter means less heterogeneity. If this continues getting sharper and sharper, eventually it's just sort of like a spike above 1, which means that all the sites are evolving at essentially the average rate. 1 represents the average rate, and all the sites will be evolving at that. As the shape comes down, you get more and more heterogeneity. So it's actually 1 over the shape parameter is a better measure of heterogeneity than the shape parameter itself. So got about 15 minutes left. I want to talk a little bit about codon models. And not going to say very much about codon models or amino acid models. I just want to introduce them to you. So to talk about codon models, I need to just briefly remind you of how the genetic code works. Most of you probably already know this, but if you have a DNA strand, it's a double helix, and so one of the strands is referred to as the coding strand and one's the template strand. And the template strand, when it undergoes transcription, you get a messenger RNA that is the complement of the template strand. So the T's change to A's and the A's change to U's in the messenger RNA. Then the messenger RNA is translated by the ribosome into a polypeptide, and the nucleotides are taken 3 at a time. These are called codons, these 3 triplets of nucleotides in the messenger RNA. And they're converted to an amino acid using a genetic code. And here's a universal genetic code table. It's not really universal, but it's a common genetic code. And this tells you that if you see UUU in the messenger RNA, then the ribosome should put in phenylalanine as the amino acid. And so this determines all the 64 possible codons. It determines what amino acid will go in. And 3 of these are stop codons, which means that the ribosome would interpret that as the end of the polypeptide that it's making. So how do we model, how do we incorporate the genetic code into a model? There are 2 papers that were published back-to-back in 1994, Musengat and Goldman and Yang. And these basically presented very much the same model. There were a few differences between the models. The Musengat model is a little bit simpler, so I'm going to use that as an example, but Goldman and Yang model has become sort of the de facto standard these days. This model basically has a rate matrix that's 61 by 61. We leave out the 3 stop codons and just make 61 states. And the states, instead of nucleotides, they're codons. So TTT is a state, TTC is a state, TTA is a state. And below each of these codons, I've put the amino acid that they code for in the universal genetic code table. So here's the diagonal elements are just minus the sum of the rates in the rest of the row. So I'm just going to leave those out. This would be very ugly to put those in at this point. But if we take a look at some of these examples of the rates in this rate matrix, the synonymous substitution here, we've got a phenylalanine that changes to a phenylalanine. So it's a synonymous substitution, and we put in the synonymous rate alpha in this case. And then there's one base that's changed from a T in the 3rd position to a C. So we put in pi C here as in the rate as well. So the rate of this particular kind of substitution is alpha times pi C. Let's take a look at this one now. So this case, we have a C changing to an A, so we put a pi A in, but this time it's a non-synonymous substitution. We have a change from a phenylalanine to a leucine. So the amino acid is changed. That makes it a non-synonymous substitution. So we put an alternative rate parameter beta in for the non-synonymous substitutions. So this allows us to get an idea of what the ratio between the rate of non-synonymous and synonymous substitutions is if we estimate these separately. And the pi's are here to make this matrix time reversible, as we've seen before. There are a lot of zeros in this matrix, so we put a rate of 0 if more than one nucleotide changes is observed. So in this case, we have CTC changing to GTG, and basically every one of the 3 nucleotides has changed to something else. And this basically says that you can't have multiple substitutions in one instant of time. This is an instantaneous rate matrix. There can be only one event that happens in an instant of time, and so the probability of having 3 substitution events happening in that instant of time is 0. This doesn't prevent us from changing eventually from CTC to GGG. It just means that it happens over a longer period of time. So these zeros do not exclude those kinds of changes from happening. It just means that you have to have a larger period of time for them to happen. So codon models are cool. They're expensive to calculate, but they're cool because they give you this insight into selection. So if we let omega equal this ratio of non-synonymous to synonymous rates, so once again, we're back to the non-synonymous to synonymous rate ratio versus ratio, is that you can review what I talked about earlier with the transitions, transversions, to understand the difference there. But this is the rate ratio. And if you look at that rate ratio, it tells you a little bit something about the mode of selection. So if omega is really low, it means the non-synonymous changes are really rare compared to synonymous changes, and the gene is probably under strong stabilizing selection. So nucleotide substitutions rarely change the amino acid. So most of your changes are going to be at the 3rd position sites, which end up being synonymous much of the time. So this is sort of true of functional protein coding genes. The omega, if omega is 1, that reflects neutral evolution. The rate of change is the same regardless of whether the amino acid is changing. So basically selection doesn't care what happens in that case. And this would be true of pseudogenes. The synonymous and non-synonymous substitutions occur at the same rate. If a gene is no longer being used, then selection doesn't care what happens to it at that point. And so you get basically this equal rates scenario. But then sometimes you see positive selection where omega is greater than 1. And this means that nucleotide substitutions often change the amino acid at a particular site. And so this would be true particularly of envelope proteins and viruses that are under active positive selection because they're trying to evade the host being able to recognize them. So they constantly change their envelope to stay under the radar, so to speak. So codon models are cool because you can interpret the results in meaningful ways with respect to selection. So I want to spend a few minutes talking about a technique that is a little esoteric and obscure, but it's important in phylogenetics, and you'll see it discussed a lot in technical papers. And so I want to try to explain what's going on with this diagonalization. So for simple models such as Jukes Cantor 1969 model, it's possible to obtain formulas for transition probabilities, and we've done that. We saw how to derive both of these forms of the transition probability in part 1 of the series. And these models are great when teaching phylogenetics because I can have my students calculate likelihoods of small trees by hand using these formulas and just a hand calculator. But for many models, including the GTR model, the codon models, and most biologically interesting models, it's not possible to obtain transition probability formulas. Instead, we must extrapolate these rates in the Q matrix into transition probabilities numerically. We must take a Q matrix comprising 16 floating point numbers and convert it to a P matrix with also 16 floating point numbers without going through this intermediate of having these nice formulas. There's actually a very simple looking formula that can accomplish this, but unfortunately it's not the kind of formula that you can plug into a hand calculator. It says that the transition probability matrix can be obtained by raising E, this constant E, to the power QT, where Q is the rate matrix of instantaneous rates and T is the amount of time that has elapsed. So we can't actually plug this into a calculator, but we can use this formula to calculate transition probabilities numerically. So in order to do this, I want to go sort of reduce the Jukes-Cantor model to an even simpler model that just has two states. So we have either zeros or ones. So our rate matrix is now just this very simple rate matrix, and here's the corresponding P matrix. It's simple enough that we can get formulas for these, but I want to show you basically how you would do this numerically as well. So the state space is so simple that basically the state frequencies pi 0 and pi 1 have to follow this line. So either pi 0 is 1 and pi 1 is 0, which means you have all zeros or a 0 at a site. And if pi 1 is 1, it means you have 1 at a site. So this case here would be all ones would mean that we're sitting at pi 1 equals 1. It means that the probability, the equilibrium frequency of 1 is 100%. If we let this sequence evolve for some time, like we did in part 1, I showed you an animation of this sort of thing happening, then that dot will move to the equilibrium point, which is right in the middle, where pi 0 equals pi 1 equals a half. So it has to follow this line because pi 1 and pi 0 and pi 1 have to add to 1. And so if you reduce pi 1, you have to increase pi 0 correspondingly in order for that rule to stay in effect. So we're following this line, but we're always going toward this equilibrium point, whether we start from this end and go this way or that end and go that way. So if we start at the other side where we have all zeros and we let it evolve for a long period of time, we're going to go to the equilibrium point again where you have an equal mixture of zeros and ones along this way. So the trick is this P matrix tells you basically how far to move from any given point toward the equilibrium. If the branch length is really long, it means you'll move basically all of these terms with ease go away, and you end up with just 1/2, 1/2, 1/2, and you end up with this at the equilibrium point. If the branch length is very short, then you end up moving just a short distance. And so in order to do this numerically, we have to diagonalize the Q matrix. And what that means is we convert it into a matrix of eigenvectors. And you can see that if we diagonalize both Q and P, the matrix of eigenvectors is the same in both of these. So that just tells us something about the direction that we have to move. And we always move in the same direction, whether we move a little bit or a lot. Basically, we're always moving toward that equilibrium. So the eigenvectors tell you the direction regardless of how much you move. And so that's why the eigenvector is the same between the Q matrix and the P matrix. It's just telling you the direction that you have to move. And the inverse of the eigenvector matrix is also comes into play, and that's the same for both P and Q matrix. What's different is the eigenvalues. So the eigenvalues are on the diagonal of the central matrix, and those are what's different. And basically, this formula basically says to extrapolate by exponentiating the Q matrix times T. So if we take the exponential of a matrix, the way to do it is if we can decompose it into eigenvectors and eigenvalues, you take the exponential by just exponentiating the eigenvalues themselves. And so we take e to the 0 that times t, that becomes this one, e to the minus 2 beta t, that becomes that one. So we can exponentiate the qt matrix by just exponentiating the eigenvalues, and then we put everything back together again. We do this matrix multiplication, and we'll get the p matrix back. So that's in effect what's going on when we do this. So I have a little demonstration that I want to show you. Hopefully everybody can see this. So this basically shows the eigenvectors and the eigenvalues and the inverse eigenvectors. And if we have a certain expected number of substitutions, what I just want to show you is graphically what's going on here. So I'm just going to invent state frequency vectors. So pi 0 is 0.42 and pi 1 is 0.58. And then if we multiply this vector times the inverse eigenvector matrix, that has the effect of basically rotating everything so that we're in a coordinate system that has the eigenvectors as axes. And this is really convenient because the next step, multiplying that vector times the diagonal eigenvalue matrix, basically just scales these. So we're going to move the point along these two axes based on these scaling factors. So the x-axis, we're not going to change at all because we're multiplying by 1. And the y-axis, we're going to multiply by 0.37. And you'll see that happen when we do the scaling. So we haven't changed the x-axis at all, but we've reduced the y-axis to that point. And then we finish by multiplying by the eigenvector matrix. And that has the effect of rotating everything back to the original coordinate system. And now we've effectively moved that point closer to the equilibrium by doing this transformation. So what I want to do is just go through this again, but I'm going to make the branch length really long so that we're going to go basically all the way to that equilibrium point. So I'm going to choose a random point to start with. Notice now that the eigenvalues of the transition probability matrix are 1 and 0, which means that we're not going to change the x-axis at all, but we're going to basically totally move the y-axis to the origin. We do the rotation. Here's where we do the scaling. And now we go all the way to the equilibrium point and then rotate everything back. And so when we do this eigenvector diagonalization, basically it's to make it easy to transform the point so that it approaches the equilibrium at the, it goes the proper distance toward the equilibrium. Just makes it easy to do it numerically. And that diagonalization app is on the website there. If you refer to that, you can see how it's done. So the empirical amino acid models is the last thing I want to talk about today. I'm just about out of time, but I just have a few things to say about these. So these are very different models than all the models we've talked about so far. These are empirical models, which means that you take a bunch of sequences and you obtain the Q matrix from those sequences, and then you just use that Q matrix directly to create transition probability to extrapolate to different amounts of time and use it in your likelihood calculations. And so, so one nice thing is once we're freed from having to have formulas for transition probabilities by the diagonalization method, we can use a great variety of Q matrices. So basically, in 1978, Dayhoff, Schwartz, and Orcutt identified a bunch of accepted point mutations using closely related sequences. So they chose these closely related sequences so there wouldn't be a lot of multiple hits. And they produced this matrix, which you can sort of think of as a proxy for a Q matrix. And then they obtained transition probabilities from this by extrapolating this Q matrix over larger amounts of time. And this paper by Kosiol and Goldman in 2005 does a nice job of discussing ways of estimating a Q matrix from these numbers. But basically, we're using diagonalization sort of backwards. We're starting with some evolution that's happened over a certain amount of time, and we're going to extrapolate backwards to get a Q matrix from that. The Q matrix for these models is often presented in the following form, factored into sort of the symmetric matrix of exchangeabilities and a set of state frequencies. And these models can often be improved by replacing the frequencies with frequencies that are more appropriate for your particular sequences, but retaining the exchangeabilities, which tell you something about the average amount of time that, for example, cysteine changes to some other amino acid. If we look at the GTR matrix, revisit that, we can also break the GTR matrix into exchangeabilities and frequencies in much the same way. So here's the diagonal matrix of frequencies. Here's the exchangeabilities. There's that mu parameter that's present in all of these. You have a symmetric matrix of exchangeabilities, the diagonal matrix of frequencies. We multiply all this together, then we'll get the diagonal matrix of the original matrix back. We won't get the we'll get the off diagonal elements, but we won't get the diagonal elements. But those can be easily calculated from the off diagonal elements. And so we're just doing the same thing for a much larger matrix when we do the protein models. So we can get an empirical Q matrix from many closely related pairwise comparisons, and the Q matrix can be extrapolated to any desired value of T using the diagonalization to generate a P matrix. So we can use this in calculating likelihoods by using that diagonalization method to numerically calculate the P matrix. These models basically capture generic features of protein evolution, but the Q matrix does not necessarily reflect your particular sequences. You're taking a generic matrix that reflects proteins in general and applying it to your particular proteins, which may not evolve in exactly the same way. So there's one limitation there. But frequencies can be swapped with more appropriate set that are locally estimated from your particular data set to sort of tune this a little bit to your particular data set. And then, like the other models, there's been a series of improvements. The JTT model in 1992 is based on a much larger protein database. The WAG model in 2001 started using maximum likelihood to estimate the Q matrix, which did a better job. It didn't overlook the fact that there were some multiple hits in the closely related sequence pairs. And then the LG model uses maximum likelihood and rate heterogeneity as part of the model to estimate the Q matrix. So it does a better job of estimating the Q matrix by accounting for rate heterogeneity. So I've gone a little bit over, so that's the end. I've just got a couple of slides of the papers that I've cited that will make it into the online presentation, but that's it for part 2.
Thanks, Paul. That was an awesome whirlwind tour of I wondered, so time reversibility went by a little bit quickly. Could you say a little bit more about why that's a useful assumption to be making?
I'm not sure how much I can say about that. It makes it it makes it easier to get the diagonalization, because if you have a time reversible Q matrix, then the diagonalization, I don't want to get into too many technical details, but it avoids things like complex numbers in the diagonalization. But there are alternatives besides diagonalization for handling non-time reversible models. And so basically, I'm not exactly sure that I know the answer to why we've been sort of so fixated on time reversible models. One explanation is in the old days, we didn't actually look at rooted trees that often because we were trying to do a search over tree space, and there were far fewer unrooted trees than there were rooted versions of those trees. And so it sort of made sense to use a time reversible model if you're not going to use a rooted tree, because you can just basically root it arbitrarily at any point for the likelihood calculation. But now that computers have gotten faster, algorithms have gotten better, we have GPUs that are at our disposal, and it makes these calculations a lot easier, even using non-time reversible models, and you add more realism to the models. And so I suspect that over time, the concern over time reversibility is going to go away more. You probably have more of an insight into this than I do in terms of in practice. But that's about all I can say about it, I think.
Yeah, well, I guess one useful thing is that, like, if you yeah, like you said, you can move the root around, and so that means if you do some tree rearrangement, then you can sort of keep those partial calculations that you made, and just recalculate your likelihood. But yeah, we're getting on the technical side of things.
Yeah.
Yeah, well, I don't see any questions on Twitter or on the chat, but I think we can just look forward to the next session. Let me remind people.
Yeah, the next session I'm going to start talking about Bayesian phylogenetics, and so the next session I think will be kind of fun because I'll talk about Markov chain Monte Carlo and explain a little bit about how that works, and I'll try to explain the Bayesian approach in a sort of more intuitive way. I've got this app called the MCMC Robot that I've been using for many years to explain how MCMC works, and we'll play with that next time quite a bit. And so the app is kind of like a computer game that teaches you most of the power and the pitfalls of MCMC, so you sort of can just sort of visualize then what's going on when you do more complex cases like phylogenetic MCMC. You can sort of understand what's going on by remembering what it looked like in the simple MCMC robot simulation.
Awesome. Yeah, I'm looking forward to that on June 20th.
Okay, sounds good.
Thanks, Paul.
Thanks.